All right, everybody, we have one finalist team left. Presenting for Team Cellucoat is Zainab Hakim from Canada, currently studying biomedical sciences at the University of Calgary. You've been waiting so patiently. Thank you so much for joining us today. Welcome to Grand Rapids. How are you feeling?
Feeling all right, a little nervous.
All right, well, you've got this. We're looking forward to your presentation. Go ahead and take it away.
Canadians love fresh fruit, but our landfills do not. According to the UN, Canada loses over $50 billion in annual losses due to food waste. But this problem isn't limited to Canada, as over the 3-day Wege competition, over 10 million tons of food will be wasted all over the world. But the food waste problem in North America is unique because the produce distribution pipeline can take up to several weeks, leaving produce susceptible to rotting and bruising, reducing the amount of time that people have to eat their produce before having to throw it away. It's clear that current preservation methods aren't cutting it. We need a longer-lasting preservation solution. However, food waste is not our only problem. The food industry is heavily reliant on single-use plastic packaging, which ends up in our landfills, causing devastating environmental consequences. As of June 2022, the Canadian government joined 77 other countries' efforts to ban or reduce single-use plastics. And according to consumer interviews, there is a majority of consumers that agree that plastic waste is excessive. We need a sustainable alternative. Our team understands that the plastic and food waste problem is urgent, so we thought to ourselves, how can we use food waste to develop a sustainable and affordable plastic packaging alternative? This is where Cellucoat comes in, a packaging solution that keeps your produce fresh from the fields to your fridge. Our vision is to use food waste to develop a sustainable plastic alternative to help the world reduce both food and plastic waste. So how are we going to do this? We're going to use produce waste and break down its sugars to help us build our base material, bacterial cellulose, a natural food-safe biopolymer made from the same bacteria found in kombucha. We're then going to use genetic engineering techniques to customize our base material with preservative proteins and bioplastic proteins to give our material preservative qualities and plastic-like flexibility. We then shape our material into boxes, which is suitable for transporting produce and being stacked during shipment. From peel to package, because Cellucoat's properties are akin to plastic, members of the produce supply chain are able to make the switch to a more sustainable alternative without compromising existing systems set in place to transport produce. Now, moving on to our materials. Each of our materials can be broken down into each step of our production cycle. First, we source our produce waste from our partners at local grocery stores. Next, a partner at the University of Calgary donated a starter culture, which gives us a continual source of our material. Our engineering team then developed a bioreactor that we can have to optimize our material production. Lastly, our design team partnered with a biodesigner to create a natural dye out of food waste along with a 3D printed mold that allows us to make our material into boxes. From peel to package, all of the materials that go into Cellucoat are generally recognized as safe by the FDA. To promote a circular economy, Cellucoat uses food waste as an input in its production cycle. We're able to do this because produce waste is lost throughout the entire produce production pipeline. And so what we do is we take this waste and we create it into a food waste feedstock to grow our material in. We were able to prototype this method and through donated orange scraps from a local Save-On Foods, and we found that we can reduce up to 60% of production costs using this method. Not only does Cellucoat provide a means of reducing food waste, we provide a novel means of using unavoidable waste. This allows us to shift the way that we are addressing the food and plastic waste problem. Not only that, but Cellucoat provides a means for members of the produce supply chain to reduce upwards of 40% of losses due to spoilage during transportation. At this point, Cellucoat is more than just an idea. We've gone through several stages of prototyping, starting from a small box that can hold no more than a few coins to a full-size raspberry container. We were able to test our material's preservative properties through showing that it can kill fungi and bacteria that are spoilage-causing. We were also able to show that it can be customized to be strong or flexible through mechanical stress testing tests. And that shows that Cellucoat can be catered to different types of packaging. Our next steps are to customize our aesthetic qualities for consumer appeal. In order to bring Cellucoat to the market, we plan on investing in materials to expand our lab and production capacity, continuing our partnerships with industrial professionals to develop our MVP, increasing our supply of fruit waste media by inserting ourselves into existing pipelines designed to divert food waste and secondary materials, and most importantly, continuing our customer discovery to ensure that our product serves consumer needs. Cellucoat's competitors are plastic and other sustainable materials like cardboard and seaweed-based alternatives. However, plastic is being phased out in legislation currently, and sustainable materials are often just not durable enough to withstand the mechanical and other requirements for packaging. However, Cellucoat's strength, preservative, and aesthetic qualities can all be catered to our buyers' needs, which is something that one-size-fits-all packaging just can't do. Thus, Cellucoat provides a viable and sustainable packaging alternative. Of course, for a material to do well on the market, it must be cost-effective. And even though plastic itself is cheap, because of legislation and negative consumer opinion, retailers are shifting towards more sustainable alternatives, like PLA, a renewable plastic. PLA costs about $30 per kilogram to produce, but the only issue is that it's not compostable, which only contributes to our ever-growing waste problem. So we conducted a techno-economic analysis on Cellucoat, and we found that our base material would only cost $25 per kilogram to create, while our fully customized material with integrated aesthetics and preservatives would only cost $33 per kilogram to produce. So far, our team has been hard at work, raising $19.5 thousand in startup funds to reach our goal of $50,000 in startup funds. With that, we plan on, when we do introduce Cellucoat to the market, we estimate that within the first 5 years of releasing it, we will rank in a net revenue of $3.7 million. In order to bring Cellucoat to the market, we are currently in talks with members of the produce supply chain, such as Loblaws and Star Produce, who've expressed interest in our product and are willing to participate in future business endeavors. We've partnered with members of the Calgary Waste Management's facilities, and we were able to prove that our product is compostable in industrial composting facilities, unlike other sustainable materials who are marketed as biodegradable but can't actually compost in home and industrial composting systems. We wanted to share our passions for waste reduction with our partners at the Calgary Waste Management. And after communicating with members of the composting team, we found out that many Calgarians, as well as Canadians, often struggle with figuring out which bin, waste, compost, recycling, to put their waste in. So we created a series of educational initiatives, such as recycling posters that we put up in public spaces, as well as a series of waste management tips that we put up on the Calgary Garbage Day app. Upon assessing our impact, Cellucoat has a positive effect on the environment because we are replacing plastics and we are able to be composted. Our project fits within the UN Sustainability Goals 2, 12, and 13 because we're not only reducing food waste, we are providing a viable and less resource alternative to plastic, which plastics production itself is resource intensive, environmentally damaging, and creates a lot of greenhouse gas emissions. Cellucoat averts all of those issues. This project wouldn't have been possible without our talented team of interdisciplinary undergraduate students in various STEM fields who share a passion for business, research, and industrial design. This project also wouldn't have been possible without our wonderful mentors in academia and industry who gave us all the expertise needed to be successful. In the next 5 years, we're working towards developing our prototype, garnering funding, and getting a business license as well as a patent. So, help us help you. Keep it fresh from the fields to your fridge. Thank you very much.
Excellent work, Zainab and Team Cellucoat. Thank you so much. Judges are going to chat for a minute. Wow, fantastic. This is also an issue near and dear to my heart, so thank you so much for your presentation, your effort here. Can you tell us a little bit, first off, about your volunteer opportunity? We heard about it in your bio. You volunteer with the pediatric. Tell us about it.
Right, yeah. So I am a research assistant at our local children's hospital.
Good for you.
Like all undergraduate students, I have little direction in my life. I want to figure out what I'm doing. And the prospect of graduation without knowing what I'm doing is a little anxiety-inducing. So I am dipping my toes in everything. I'm trying to figure out what I want to do.
Good for you.
And this was one of the opportunities I was trying. I was wanting to see if I wanted to be a researcher in medicine. And Cellucoat was also something that I was doing while I was doing this research opportunity. And I am very thankful for Cellucoat for giving me a bit of more direction in life. I'm finding my passions in the biotechnology industry now.
Good for you. Well, there's just such incredible opportunity and need. So tell us, Zainab, about how your team came together, what the inspiration was, and how you worked together as a team to achieve something so important.
Right. A majority of my team actually never knew each other before we started this project. And we actually got together during a summer research term. And we started developing this project as a genetic engineering project, where we were developing a new preservative protein. We were expressing it in a chassis, which is E. coli. And we were also producing a bioplastic in a chassis similarly. And we were wanting to figure out how can we use these two things in an actual applicable setting, because science can't be useful unless you're bringing it to the public. And so this is where we conceived Cellucoat.
Fantastic, great. Okay, judges ready for Q&A? All right, take it away.
Hakim, thank you so much. This was an awesome presentation. Your enthusiasm is like, phew, filled the room. So well done. I have a question about the choice that you made in collecting the food waste. Why did you guys choose the supermarket and not the transportation, for example, or the homes? Because in the transportation process or the homes is actually where the highest amount of food waste there is. And when the food is already in the supermarket, it could be taken to a food bank or it could be transformed into jams. So I'm wondering about your choice there.
You are absolutely correct. We have our partners at the local Save On Foods, and we actually discovered some of the secondary materials that could be made from food waste at supermarkets. You know, those oranges that you see going bad on the benches, they actually create juice that you might buy at the supermarket. And the reason why we chose to make our prototype out of those oranges that were going bad at the supermarket was just because it was nearby our lab. Ideally, when we are scaling this up to a mass industrial production, we will be sourcing our produce waste from industrial plants that use food as a product, as well as produce distributors, because they aren't able to sell the materials to retailers that go bad. They have to send them back, and that's a loss for the produce distributors. So we can make sure that they aren't experiencing a loss by shipping it to us.
I have a question for you. Two parts, actually. The first part is around the aesthetics and performance of your material. So the aesthetics, I want to know if you've done any feedback from people and consumers or grocery departments in terms of their interest in it. It's very different than a kind of plastic look and feel, so I'm curious about that. And then secondly, I'd like to know if you've addressed any of the classic issues when it comes to biomaterials around water barrier properties, fungal growth, that kind of thing. So that's the first in terms of performance. The second in terms of scale, bacterial cellulose, how does that scale? So it's a grown material that has a time dynamic. I'm curious of how long it takes, how the bioreactors will scale up in your vision of the future, and how that feeds into the kind of cost competitiveness that you've calculated.
Lovely question. I'm going to first start off with the first question. You might have to remind me about the second one. But in regards to you remind me of the first question?
Aesthetics and water barrier properties.
Lovely. Okay, so aesthetics were initially something that we wanted to consult a member of the produce industry about. So we consulted with a member of Star Produce, Chris Clark, and he told us that many retailers actually prefer to have their packages transparent with a color that's the same as their produce. So if it's strawberries, transparent with a pink hue, because it helps hide some of the aesthetic deformities of a produce without reducing its sellability. And consumers want to be able to see their produce, so they want it to be transparent. So we were able to develop a post-production treatment that makes our bacterial cellulose both transparent as well as integrating a natural dye, so it does not reduce its compostability like plastics, which can't be recycled once they are dyed. In regards to its water absorption, because we also do a post-treatment that changes the structure of bacterial cellulose, that makes it more water-resistant or hydrophobic. And the integration of a bioplastic, it's called PHB, it also increases its hydrophobicity. And changing the ratios of PHB also changes the hydrophobicity. So for materials that are more likely to have more moisture, like berries, we would increase the ratio of PHB or prolong the amount of time that it undergoes a post-production treatment. Your second question?
And then the scalability of the bioreactors and the process that you have.
Lovely. So the bioreactors were put in place to ensure that we can autonomize production. So we were reducing labor costs. And in regards to production, think of it kind of like wine. You have a bunch of wine in the cellar, and then it's producing, while you have a bunch of wine on the shelves. So we're able to shift the way, like push forward a product while we're growing new ones. And the production cycle takes less than 2 weeks, so the entirety of growing and post-production. And so getting it to market would mostly be reliant on how fast we can grow it in our bioreactors. And we are in the process of consulting with material experts at our university to optimize our production and reduce production costs. Great question.
Thank you very much.
I have a question regarding, I love that bacteria though. I love seleno. I eat them, you know. Perhaps you have heard about nata de coco.
Right.
Yeah, they make it in Philippines,
They do.
Thailand, and it's a big commercial operation all over, you know, the last 30, 40 years.
Mm-hmm.
The ingredient they use to make cellulose is coconut water and acetic acid. Tell me about your, what do you use to feed those bacteria?
So initially, our starter culture we got from a member at the University of Calgary, and it is called Zainab, that's the bacteria name. And same bacteria that you find in kombucha, you drink it. And we initially grew it in a traditional HS media. It is very expensive, that media. And so we thought to ourselves, okay, how are we going to reduce production costs? So we took inspiration from nata de coco and kombucha, and we thought, since it can be created from just simple sugars, we can also do that with produce waste. And so we created a novel food waste feedstock by breaking down sugars down into its individual sugar components like glucose, fructose, sucrose. All of that the bacteria can grow in, and it actually does better to grow the cellulose in. It grows even stronger cellulose than if we were to grow it in the traditional media. And so it's a lovely question. We can always learn a lot from tradition and culture.
Thank you. So I have a question on over here. So there obviously will be a very wide variety of inputs of produce, you know, discarded produce. Are you going to be sensitive to that mix in terms of your process? It doesn't matter at all what produce hits your process?
That's a great question. So we initially prototyped with oranges because that's just what was available to us. Canada has a really big apple market. We are right next to BC, British Columbia, and they have a really big apple market. And so ideally, our main source of produce waste would probably be from apples, peaches, berries that would be grown in the areas around Alberta. And we aren't really sensitive to what type of produce goes into our material because it's all broken down into glucose. Different produce has different glucose ratios. Some of them have more of one type of sugar than the other, but bacteria isn't picky, likes to eat all of it. So
Thank you.
It's all good.
Hi, Zainab. A question for you right here. Can you tell me a little bit about the anticipated production process you would use to scale up? I mean, what kind of, is it vacuum forming, or what kind of mechanical process would you use? And have you extrapolated the difference between plastic processing and your process for water impact and energy impact?
Lovely. That's a great question. We consulted with another member of the produce supply chain. He's also a member of Loblaws, and as well as the bio designer, who told us about different ways that plastic is made. And we aren't going to be following the injection mold method, because that's just not how bacterial cellulose is produced. We produce the base wet material. It's like a big slab of SCOBY, if you've ever seen it. And then we dry it in a mold. And so this drying process is not energy intensive at all, because we are using wooden planks that naturally suck out the water out of it and it evaporates over time. It's quite quick because we are using wood, and it allows us to, once again, autonomize the production process to lower labor costs. And sorry, was there another part to your question?
Energy and water.
Right, energy and water. In regards to water, there does need to be a little water input because we are growing bacteria. But the media that we are using can be reused. And so it's a bit of a one-time thing where we put in the water, and then you just have to occasionally balance the pH and other minerals inside of there by changing the water ratios. But otherwise, whatever is in the bioreactor will be carefully balanced. And so we're not using more water than we need. But we will be consulting with environmental experts at the University of Calgary to help us determine those exact measurements so we can ensure that Cellucoat is truly environmentally friendly.
Sadly, we're running out of time, but I do have a quick, slightly playful question. I do have a whole heap of questions, but this one's going to finish off because we've only got 19 seconds. Can I eat it?
Yes, but you shouldn't. It is totally food safe. We purify it. There is no bacteria left in there. And so we tried growing it in a dish. It didn't grow at all once we purified it. You can eat it.
But probably not, but it wouldn't be unsafe for me to eat it.
You can eat it, yeah. But it's kind of like how you can eat a SCOBY, but you don't want to.
That sadly sees us up to the time of your questioning.
Yes, thank you very much, everyone. It was lovely to have me here.
And Team Cellucoat, awesome. I'm particularly excited about bacteria now. Thank you so much.